Thermodynamics is the study of energy. Really like the movement of energy. 3 laws of thermodynamics. Energy of the universe is constant. You may have heard this before, usually stated like energy is never created or destroyed, mass is never created or destroyed, that kind of thing. All the same thing. The amount of energy at the beginning of the universe is equal to the amount of energy at the end of the universe. It doesn't go away or come into existence. Energy, it always flows from high levels to low levels, right? From hot to cold. So if you have like an ice cube, and you put that ice cube in your hand, you got a cold ice cube, you put it in your warm hand, your hand is not going to cool that ice cube off anymore, right? The heat from your hand is going to move into the ice cube and warm the ice cube up. Just like if you have a hot stove and you put your hand on the hot stove, the heat's going to flow from the hot stove into your cooler hand, which is a bummer.
Is it like the opposite too? Like the ice cube makes your hand cold?
Cold doesn't exist. There's no such thing as cold. Just like, so there's two things important. There's no such thing as dark or cold. Okay? Dark is an absence of light. Cold is an absence of heat. So it's not that the ice cube makes your hand cold, it's that the ice cube sucks out the heat. Okay.
Why is there no such thing as dark?
Because it's an absence of light. I can't make dark. The only way I can make dark is by stopping light from entering an area. But I can make light anywhere. Does that make sense?
Yeah.
That's fine, you don't have to understand. Okay. Do you like organize? I got something you can organize. No system can reach absolute zero. That's kind of funny. Because there's actually a lot of money and research and intelligent people that are trying to prove that law wrong. Right? Absolute zero, negative 273.15 degrees Celsius. No free energy left in an atom. Absolute zero. The problem with that is, if you have no energy, then maybe you have no mass or volume, and you cease to exist. So you can't really cool something off and make it cease to exist. But they're working on it. They've gotten really close. They've gotten really close. Temperature is the average energy of particles. Temperature is an energy. Is like a measure of the amount of energy in a substance. So you have a cup of water. Matter of fact, I have a cup of water. You have a cup of water. You put a thermometer in it, and you're like, oh, that's 23 degrees Celsius. Well, on average, there may be some water molecules with energy equivalent to 60 degrees Celsius. There may be some water molecules with energy equivalent to 5 degrees Celsius. But overall, average 23 degrees Celsius. Heat is the flow of that energy due to a difference in temperature. So heat is a flow of energy. It's a moving. You feel heat because energy is moving from something warmer into your colder hand. All right. Specific heat. This is a good one. This is a cool one. I like this one. It is the amount of energy required to heat 1 gram of a substance 1 Celsius degree. Gonna let that soak in. So it takes, in joules by the way, so it takes 4.18 joules of energy to heat 1 gram of water 1 degree Celsius. Q equals mc delta T. Q is the energy or the heat. It's the heat, the flow of energy. Equals the mass times the specific heat times the change in temperature. Delta means change. You gotta just start seeing that. You're going to see that a lot. So the change in temperature. That's why when you go to eat a hot piece of pizza, the crust may be cool, or at least just warm, but you go to bite it and the cheese and the tomato sauce burns your mouth. Because the cheese and the tomato sauce are made of mainly water, and that holds a lot of energy in there, so it puts a lot of energy into your mouth. Whereas the dry stuff isn't going to be able to hold as much energy, and it's going to give you all of the energy it has, but it's just not going to be enough to burn you. Okay, we are a scientifically advanced society, I feel. We got all these fancy things. We got people living in space. We got all this crazy stuff going on. We can put on fake limbs onto people. What do we use to cool our automobiles?
Water.
I use water. Right. Nuclear reactors. What do nuclear reactors use to cool themselves?
Water.
Water. So water can hold a ton of energy. Okay? All these crazy things in the world, water is still the best. Okay, so here's how you use the equation. How much energy will be required to heat up 100 grams of water from 20 degrees to 40 degrees? Q equals mc delta T. Q is what you're solving for. Equals M, the mass of your water, times C, the specific heat of your water, times delta T, the change in temperature. You went from 20 to 40, the difference is 20. Multiply them all together, you only get 3 sig figs. So your answer is 8,360 joules. So now you get to try one on your own. Here's another one. Try this one. Sample of water requires 200 joules of energy to be heated by 17 degrees Celsius. How much water is being heated? So how much energy is needed to heat 10 grams of iron from 22 degrees Celsius to 31 degrees Celsius? Hint, the specific heat of iron is 0.45 and sig figs don't apply to constants. This is the important part. This is why, right? Why do you have to learn this? Why do you need to do this? What are we going to do it for? This is what we're going to do it for. This is the labs that we're going to do it for. Heat loss equals heat gains. What that means is, when I got this piece of metal all nice and toasty, and I put it into the water, the metal lost a bunch of heat. The water gained a bunch of heat. The amount of heat that the metal lost is equal to the amount of heat that the water gained. So you can go mc delta T equals mc delta T. Your mc delta T of your metal equals your mc delta T of your water. A 20-gram sample of aluminum, let's just pretend this is aluminum. A 20-gram sample of aluminum is heated to 100 degrees Celsius and then is dropped into some water. The water was 20 degrees. That metal heated it up to 21 degrees. How much water was in the cup? Well, mc delta T equals mc delta T. So I know my mass of my metal, my C of my metal, and my change in temperature of my metal. I was at 100 degrees. I finished at 21 degrees. That's a difference of 79 degrees. Okay, I can do that and find my Q of my metal. So the Q of my metal is going to equal the Q of my water. So Q of my water equals mass of my water times specific heat of my water times change in temperature of my water. And it went from 20 to 21. So you do the math, you find that you have 336 grams, which is 336 milliliters. So now try the next one on your own. What's up, Kelsey? So how I like to do these is I like to just fill it out. Just do it. So mc delta T, I always like to write this. And this is going to be really helpful because a lot of this class is all just equations. So, and then you start filling out, we can call this the water, and we can call this our metal. And so water, we know we have 100 grams, we know it's 4.18, and we know it rises 0.2 degrees. And then you can fill out the metal side with what you know, and solve.
So, it's heated.
Come on, guys.
Do we put a 0 first? Do we put it in the decimal?
Sometimes you do, sometimes you don't, yeah. Okay, so if you do this out, 4.18 times 0.2 times 100, so you're going to have 83.6 equals
299.
equals 299C. Divide both sides by 299.
299.
I multiplied 5 by 59.8. Was it 2.8? Is that what you said?
Yes.
Enthalpy. It is the potential for energy. It is the internal energy of a system. So exothermic means your system is going to release energy. Endothermic means your system is going to absorb energy. For instance, this, right? When I had this going, I had my Bunsen burner. That's exothermic, right? That reaction is releasing energy. That's what's going on when you burn that gas. Q, it creates energy. It's releasing energy. You can feel that. If it was the other way around, if it was endothermic, your Q would be over here. And there, it would be absorbing energy, and so when you touched it, it would be cold. It would be absorbing energy. And so those like instant ice packs, where they kind of like break it apart, two chemicals mixed together, and it gets really cold to make an ice pack for you, so that's an endothermic reaction. I'll make one of those tomorrow, probably. The opposite, it's going to gain a ton of energy, but it's going to give a little bit of it back. Just needs a little bit to get started. So this is that ice pack. You break that ice pack, it's going to take a lot to get that reaction started, and then it's going to give some of it back. Meaning release some of it. But that will just be absorbed by the reaction, so you don't really notice it. Just like this, every molecule that combusts so that molecule combusts, it needs that ignition source, but then it's going to let out that. Well, a portion of that is going to be used for the next molecule's ignition source, and so on and so forth. Change in enthalpy equals work plus heat. That's it. I mean work. Let me explain it. That is a really, really easy equation. You cannot get any easier if you try. Alright? If a system is doing work, so for instance, you put gasoline in your car, you light it, it moves the pistons. Okay? Moves, right? It all moves everything, blah, 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 down your axle, into your wheels, and your car goes forward. It's also going to produce heat. So the change in enthalpy, all the energy that chemical reaction gave off, is the sum of the work it did plus the heat it produced.